Hello, we will wait for 5-6 minutes and then we will start. Good evening, everyone. So, my name is Abhishek Munshi. I'm a PMRF research scholar at IIT Jodhpur. So we are dealing with the course Design of Power Electronics. So, this is the week 7. So, in this week, we will discuss about the EMI and how EMI will generate in power electronics. And it's discuss some solution and some will solve some problem also. So basically, what is electromagnetic interference? Actually, electromagnetic interference is due to the we know that to the electromagnetic field itself. So often, as for in the lecture series, you see that there was an example over there that whenever there is an electromagnetic interference, suppose you have a noises will be arising over there, right? So we need to avoid electromagnetic interference to produce proper mm, converter. So otherwise, it will generate more and more harmonics. Okay. So basically, EMI are two types. One is a conductive EMI, one other is radiated EMI. Okay. So uh, kindly mute yourself. So basically, EMI generates due to the conductive coupling and even due to the radiative coupling over there. If you brought some sensitive device in front of that, and then the interference will create some that will hamper the original device nature. Okay, so this is what an electromagnetic interference is. Okay, so if you see from here, from the lecture, you can understand that if you measure the electromagnetic interference, this is the unit, this is the formula to measure the conducted EMI. So the unit of conducted EMI is dV microvolt, but in case of radiated, it is dV microvolt per meter, because distance at which your antenna for measuring is placed is very important in that case. So that's why you should have to consider the mm, dV per meter for in case of the radiated EMI. Okay, so if you see that in case of the EMI, we consider the quasi peak, which are sensed for measuring EMI. In case of the quasi peak, I think it was been discussed. So by using a peak detector reading, you can see that this is a quasi waveform, and from where you can able to understand the average detector reading, the peak detector reading, and this is what we require for EMI testing. So how the EMI testing lab should look like, right? So what are the EMI devices? So basically, the to test an EMI, basically the components which we require mainly is the number one is the spectrum analyzer, or we also called it as EMI analyzer. So basically, spectrum analyzer is a device which measures the disturbances with respect to the frequency. So if you have any disturbances, you will see more and more harmonics in your frequency. So this is what a spectral analyzer do. And next thing which we require for measuring the EMI is probes. So specific probes are required for this, H field probes and E field probe, that is magnetic field probe, and electric field probes are required. These are often called as near field probes. Fine. So if you use some kind of differential probe or normal passive probe, then you cannot able to see what kind of noises, what is the EMI, what is the disturbances over there. So for that we require a special type of probe, that's a near field probe. Another thing I think you will learn about this, that is line impedance. That is line impedance stabilization network. Or in short, we call it as license. So license is a kind of filter. Basically, uh, it doesn't let your disturbances or noise to enter into the device. Suppose you have a power converter over here. You have a power converter, and you are giving supply from your mains. From the mains, you are giving a supply. So this main can inject unnecessary harmonics into your converter, or in some cases if you have a bad design, or if your converter should have some kind of EMI noises, then that noise can also get injected into the mains. So that will also disturb the grids and mains, and even the from the mains, if any kind of harmonics are generated or injected to your converter, that can also damage your converter. So basically license plays a role in between of this. So we use a license in between this. So that is basically works like a filter. It doesn't let your disturbances from the mains to let into the converter, and even from the converter it doesn't allow noise to go into the supply. Okay. So that is what license is. Okay. So these are the primary devices which require, which are given over here. You can see that this is DUT, means this is the device which we are testing. Maybe a power converter, maybe something else which we want to test the EMI of that. So basically, this is within a shielded room. Okay. So this is within a shielded room. You can put this license right there. Okay. This is also within this. Okay. But your supply is outside this shielding room. Okay. So what happens? This shielding room is called screen room. This is screen room, or you can call it shielded room. So what's the functionality of this kind of room? That if you are entering into a shielded room with your mobile, you can see that there will be no network. Why? Because in case of this kind of shielded room, there will be no field. There is no magnetic field, no electric field over there. It is called screen room or shielded room. So we have to test the device. Uh, the converter which we design is on that shielded room. There is a license, as I said, license acts as a filter. So the power supply is outside this room. So from there, with the long wires, we supply it into the license, and from license it's going into the power converter or the device which we want to test. Okay. And by using the probes, which I said the near field type of probes, we can able to see the nature of this by using a spectrum analyzer which is outside the screen lit room. Okay, a spectrum analyzer is not included there. Only our device and license is there in the shielded room, and this is for measuring the conducted EMI. So if you want to see the radiated EMI, Then within the screen room, we put some kind of antennas. Okay, so for testing separate, we have to require separate antennas. So antennas are provided or needed to place at the screen room while during testing the radiated EMI. Okay, fine. We'll go more into the license, but if you have any doubt regarding this, you can ask. I'm giving 2 minutes to recall this. If you have any doubt, you can ask. Okay, fine. So we're going deep into the license. That is the, as I said, the line impedance stabilization network. So if you draw a diagram, see what is inside this license. Basically, it comes like a this kind of device without. But what is inside of it? Basically, it has line, neutral. Okay. So this is what inside this license is, and from here you have to connect your device which you are going to test, or the converter having a load itself. Okay, so this is totally the license. This is the supply where from a line and neutral are taken. So what happens? This license doesn't allow to enter any noise into the device, and if any noise get introduced into the system, then by means of these capacitors, they are confined into it. Okay. Fine. So now one question may arise that we can measure the EMI. Fine. So we can get the EMI by using the spectral analyzer by maintaining these procedures. But how could you say that that EMI has some noise that is proper? The device which I suppose prepared a converter, it is okay or not? How could you say that? So for that reason, you should have to check that there are some kind of, suppose this is your noise which you are getting and this is a standard. You have to follow that there are some standards for specific frequencies and all. So you have to get certified from that standards. There are many standards out there. There are many agencies which are giving an EMI testing uh, certifications. Number one is CSI here, FCC is there, European standards are there, ISO standard are there. You can see in some device there will be some ISO marker there. Another one is IEC standard. So you have to check that whether the guidelines is following your spectrum analysis results. If it is following, then you will get a certified that your converter is EMI compatible. So that is why we require a EMI compatible device for uh, with a certification from this kind of sources. After testing the EMI, you have to send the data and they will certify that it will be compatible. Okay. So this is what the compatibility test of EMI you can measure in this way, right? So if you have any doubt till the discussion, you can ask and try to draw it and we'll move forward then. Okay, I'm giving 2 3 minutes to draw it, and if you have any doubt, you can ask over there. Fine. I hope you all note it down. So, UI in power electronics is one of the most important concern. So, while designing a new PCB and all, you have to consider these things that how smooth your traces should be so that you don't have any noises. And other than that, there are any other factor that the parasitic components, how much it influence on that or not. So you can see from here, they say in this converter, the buck converter, we already discussed in previous lecture. So here, this is the waveform of the switch. This is the waveform of the switch where you can see that these are the switched waveform, right? So these are switched waveform. So what happens in case of the switched waveform that mm, they introduce transient noises over there, and other than that, if you have a lot of passive components like this inductor, capacitor, resistance, also they also introduce some parasitics like if you consider the equivalent diagram of capacitance, then you can see that uh, the equivalent capacitance diagram like that. It has ESR, equivalent series resistance, it has equivalent series inductance also. So these are parasitics. So in case of a resistor, if you consider it has, suppose this is the resistor. So in case of resistor, there is parasitic capacitance and it going through some lead. So lead has some inductance. Fine. So in case of inductor also, there are some parasitic resistance and even some parasitic capacitance are there. So in every component, in passive component, you will see that are not ideal. So the waveform which you are seeing, this is ideal waveform, but in reality, this is non-ideal in nature. So it has parasitics and it will introduce noises and harmonics. So if you analyze this converter in your fast Fourier transformation, you will see that if you see if you observe the FFT of this converter, definitely it has a fundamental, that is a DC component, and at suppose you are switching it at a specific frequency a phase. So at switching frequency there will be some harmonics, but other than this there will be more noise and harmonics introduced into your system at different frequencies, and you need to eliminate these things. This will introduce total harmonic distortion in your system. So by FFT analysis, you can check that how much disturbances are there that are due to the parasitics and the noises introduced into the system. So basically, there are two types of noises. One is common mode noise, another one is the differential mode noise. So let us discuss it. There are two types of noises mainly. One is common mode noise, another one is differential mode noise. Okay. So if you see in this picture, you have a line, you have a neutral. So a current is flowing through line and neutral, and there is a specific ground over there, right? So the common mode voltage generate in this case. So in this case, if you redraw it like this, line, neutral, a ground. So if you have voltage here V1, V2, current flowing I1, I2. So the common mode voltage will be V1 plus V2 by 2. Okay. And the differential mode voltage will be V1 minus V2. That is very simple. Differential mode. The common mode current I1 plus I2. The differential mode current I1 minus I2 by 2. Fine. So common mode means that is common to the line and neutral with respect to the ground. Okay. But in differential mode, there is a difference between these two line now, and this is what we call differential. So basically, how the if you see this diagram, you can able to see that this is the differential mode current. So the differential mode current is the current actually which we are reading over there. We already learned the converter design and all, and there we see that in case of buck converter there is specific current across inductor and the capacitor. That is what basically the differential mode current. Then how the common mode current will generate, right? How common mode will be introduced into the system. So basically, if you design a PCB of a converter, right? Suppose this is a PCB, so it has several components in it, right? But when you're selling it, when you are when you buy a PCB or a converter, you can see that there is an enclosure. There is an enclosure within which your PCB or converter will be there. Okay. So this enclosure has a separate ground. So this is called chassis ground. So the common mode noise and all generated, the common mode current, these are generated due to this chassis ground, because in chassis ground there is a metallic enclosure which we use, and all the other references which are connected into your circuit and your board inside of the enclosure are commonly ground into it. This is called chassis ground. So this chassis ground will create the common mode problem. That so if you see that there are unwanted capacitance which are generated between the actual point and the ground. This is our chassis ground. So this unwanted noise is basically the unwanted capacitance basically is the source for our common mode noise. Fine. So these are the two type of noise, and I discussed a little bit to it. So if you see that these are already discussed, the current paths which are in the buck converter, in the converter, that is basically your differential current path, but the common mode path will probably create a problem. So after this, if you have any doubt, you can ask, and then we will move into the solution of this EMI introduce section. Okay. So if you have any doubt, you can ask. So fine. So what are the possible solution for EMI mm, reduction? Is number one is the EMI filter. Basically, EMI filters are kind of that license which we are using in our circuit for avoiding this um, noises from the supply. Next, we can use a EMI shielded enclosure, so where no outside EMI will introduce into your system. Next, another important thing is a PCB layout. So suppose whenever you are designing a converter circuit, you have a control circuit over there, you have signal circuit itself over there. So uh, suppose you put the converter circuit at one side, the circuit at one side, and you put the control and single circuit on the back side. These are some, if your traces are not good, if you not provide proper traces in between of this and that, will introduce some kind of parasitics and noises, and this is a source of EMI introduction into your system. Okay. Next is shielded cable. We can use shielded cable where there is nothing EMI introduced due to the shield over there. Another, you can use twisted cable where this is a kind of twisted cable. In twisted cable, since these are twisted in nature, so what happens, the fields are basically cancel out and it reduce the EMI. So these are the possible solutions for EMI reductions. So next thing is that we have proper grounding. You should have to use proper grounding. Without proper grounding, it will introduce ground bounce and noise, and that will also hamper your system and provide harmonics and noises into the system. Gate register selection is also a concern issue, that in some cases you have a turn on gate register or turn off gate register. You should have to consider that properly, otherwise it will also introduce some kind of noises. And snubbers are very important. We already discussed in previous lecture that snubber is very important to avoid noises in your system in a waveform. If you have a noise, you can dump it by using RC snubber, RCD snubber. Soft switching, that is, you can use ZVS, ZCS to avoid the switching losses at the instant, and you can use random PWM also to avoid this kind of design solutions. These are to AMI design. Okay. So next, EMI filter. So you have to for EMI filter there are basically two types of chokes. We are using common mode choke and a differential mode choke. But before moving into it, we'll discuss a little bit about the dot convention so that you can able to understand these things. Uh, Fine. So so if this is my we have, this is a circular core we're discussing about. We have two possible winding directions. So and wind it in this way. So from here it is entering and here it is exiting. Okay. Or you can wind it. this way. Okay. So there are two possibilities. This is the counterclockwise, and this is the clockwise. So there are basically two possibilities. One is clockwise, another one is counterclockwise. So here, if you see in this case, current is entering and flux is there, moving in clockwise direction. Here, when current is entering, uh, moving in this direction. Okay. So different winding direction leads to different directions of flux. Different direction of magnetic flux into the core. Okay. So this direction, winding direction, has no impact if you, I can't say, if you are talking about a single winding inductor. The sense of direction of winding has no effect on the basic operation of the single winding. So this is mainly applicable in case of two winding. So let us consider. Okay. So here let us consider the wires are like this. One winding is like this. Another circuit is there. And the winding is like this. Right. So suppose you are giving a supply here. You're giving a supply here. This is V1. This is suppose V2. So here you see that for V1 there is a flux that is introduced phi 1 and this is in same direction. So phi 2 for V2 is also introduced in the same direction. So here in this case both the fluxes are in same direction. So the net flux which we introduce in the system will be phi 1 plus phi 2. Okay. So we know that V1 will be N1 d phi 1 dt, V2 will be N2 d phi 2 dt. So basically V2 will be N2 by N1 V1, right? So if in case of phi 1 equal to phi 2 equal to 5, then that is applicable. So another case can happen that if we have both the fluxes in the opposite direction, right? So If both the flux are in opposite direction, then the net flux phi 1 minus phi 2. So in this case, if phi 1 equal to phi 2 equal to, let's say, phi, so here our V2 will be minus N2 by N1 V1. Okay. So based on this, we can say the dot convention, like for phi 1 plus phi 2, current entering, and here from current is exiting. And here current entering, here current going. This is the differential mode, phi 1 minus phi 2. Fine. So now we're moving into the common mode choke, what we said. Suppose the common mode choke. So here in common mode choke, you see that there are two winding. One is like this. Now one is like this. So this is common mode. So as I said, the phi 1 plus phi 2 mode. This is 2, 3. You can name it. This is 1, 4. In between there are core. Right. So this will be the equivalent diagram for a common mode. Sure. Okay. So what is the function of this common mode choke? Basically, common mode currents are going to be attenuated or reduced in simplified way significantly because of common mode chokes. Okay. So these common mode chokes are basically used for filtering the common mode current. So they are, can say, they are almost invisible to the differential mode current. They cannot filter the differential mode current. So for that we require differential mode uh, chokes. Okay. So where a leakage flux is produced and all. Okay. So these are the equivalent diagram for EMI filter, and this is the equivalent diagram for a EMI filter having this is a Y type EMI filter. So here you can see that this is the common mode choke. This is the differential choke, and here two capacitors are used, right? This is X capacitor and another one is Y capacitor. This is the common mode capacitor, and this X and Y capacitor are basically used for filtering the differential mode voltage and current. Uh, so they are basically, this is the CX. You can consider this as CX. So this CY and CX are basically used for filtering the differential mode voltage and current. Why this is very obvious, because we put this capacitor in between of the line and the neutral, so obviously it will filter out the differential mode voltage and current. So These Y capacitors are placed in case in between the line and neutral with respect to the ground. You see, so these are basically used for eliminating the differential mode voltage and current. Okay, so in designing the CX and CY, you have to be more precautious about designing the CY. This is has special features, so design features. So you have to consider this properly. So this is equivalent differential mode EMI filter. This is equivalent common mode filter, and this is basically with differential and common mode both EMI filter. This is mostly used. This is differential mode EMI filter. This is a common mode EMI filter. So these are the equivalent circuits for EMI filters. These are the basic topologies, EMI filter topologies. One is based on the impedance mismatch technique, another is based on the filter attenuation techniques. Okay. So these are the basic structure of those things. I think we've already gone through this in this lecture, and it is obvious to understand after designing the common mode choke and differential mode choke. So if you have any doubt regarding the image filter, the dot convention which I discussed, how we decide that what is common mode, what is differential mode, how to reduce, then you can ask any questions. So I'm giving 2 3 minutes, and after which we will discuss the next topic and we'll solve some problem. Okay. So if you have any doubt, you can ask. Okay, I hope you all understand these things. Next thing is, in case of EMI filter, you have to understand that insertion loss. So, what is basically insertion loss? Insertion loss basically measures how much how much an EMI filter weakens after passing a signal at a given frequency. So, basically, it denotes how well the filter can eliminate the unwanted noise from the circuit. Okay. So, insertion loss in EMI filter is the ratio of the output signal with respect to the input signal. So it is dependent on the frequency, and it's often changes for various orders of magnitude in filters which full frequency range, making it most possible easily expressed in right. Okay. So if you're changing the frequency level and all, then the EMI filter insertion loss variation will change because it depends upon how much the filter can eliminate the noise, right? So suppose it has a capacity to eliminate noise up to a certain frequency, but you are using that for some higher frequency, then it will not have the same insertion loss ratio if uh, when we are using it for some lower kind of frequency. Okay. So why this loss is important? Why we are talking about this insertion loss? Because this plays an important role while designing and developing high frequency devices in high frequency converters. You can say whenever you are designing high frequency converters, often with a very high frequency converters, with wide bandgap devices like with CAN device and all, you should have to consider this insertion loss of your EMI filter. So that your EMI filter can meet this unique performance requirements. Okay. So as I said, there is a here I given there is a good rule of thumb to select an EMI filter within an insertion loss is that it meets the device requirement. Typically, higher insertion loss indicates higher performance. So if you're choosing an EMI filter having higher insertion loss, this is a thumb rule. So while designing choosing EMI filter, you can choose with a higher insertion loss device. It will indicate that it will perform better than that of the lower insertion loss filter. Okay. So how to measure the high insertion loss? Okay. So there are various ways. So measuring it. One, you already discussed this thing, that is spectrum analyzer. So that device can measure and display the signal strength of various frequencies with respect to the spectrum and frequency range. So based on which it can understand that how much noise and how much uh, your waveform is modulated and unwanted signals are introduced, and the spectrum analyzer can also calculate the loss measurement. We can use license as I discussed for radio frequency emission testing and EMI testing standard. License can calculate also inertial insertion loss while taking impedance into account. Then have to plot the data from other measures into the graph and check that how much it is deviating. So next, what are the factors that can impact this insertion loss? One is the configuration, electrical configuration. You should have to consider check the data sheet for higher so performance of insertion of the DMI. Next, the source and load impedance. The source and load impedance values published are then insertion loss figure that will imply that the result will more and more fluctuations in your losses insertion obviously. Load current, earthing impedance, earthing is also a factor because if you don't have a proper grounding, then also your EMI filter will introduce unwanted noise. Basically, the solutions is already discussed in design that are one of the criteria over here also. Shielding integrity, we need shielded rooms having multi-circuit for achieving high insertion loss and leakage current for common mode insertion loss. So these are the factors which can impact the insertion loss, and we can able to calculate the attenuation by the basic formula, and this is the insertion loss. I can calculate it by this formula. If you consider this is a circuit, this is the matrix inside of it, represented within this black box or white box, you can say. So I can able to calculate the insertion loss by this formula. So that is all for regarding the EMI filter design and why we need EMI filters. Why EMI? What is the EMI issue? What is the impact of it in power converter design, and why we need to understand these things? This is a very major concern, I said already. So I discussed all the topics in a light, and now we will able to solve some uh, conceptual questions I'm giving. So try to solve and participate and answer so that you can able to recall these things, and if you have any doubt you can also clear it on that moment. So this is the first question. So we have given two questions here. So try to solve it. I'm giving 5 minutes. So I hope it will be easier for you all after the discussion of so much discussion about EMI, how to use and all. Okay. So try to solve and answer it. Okay. Fine. So first question, which of the following could be a way to reduce EMI? The one is soft switching. I already discussed shielding cables, proper PCB layout. These are the solutions. Next, which of the following is true? It said that common mode choke reduces common mode current. Obviously, common mode choke doesn't affect the differential mode current. As I said in while discussing that, it looks like an invisible to the differential mode current. So it doesn't have any effect to the differential mode current and voltages. Okay. So option A and D are correct. Next, what will be the unit of EMI? And unit of conducted EMI and radiated EMI. Okay, and next, as a MOSFET gate resistance increases, EMI, what will be the nature of the EMI? The imitative insertion loss. So try to answer this. Fine. So as I said, the unit of radiated EMI should be micro dV per volt per meter. Micro dV volt will be the unit of conductor EMI because distance is an important factor while checking the radiated EMI. Obviously, if you're increasing the gate resistance, the EMI will be reduced, and if you the unit of insertion loss is decibel. Okay. Next, X capacitor are used to filter mode which mode of noise. Okay, and Y capacitor are used for which mode of noise. So select the correct statement. Next, try to answer this too. Fine. So I didn't get any answer. So X filters are used for differential mode, as I said, that is between the line and the neutral, and Y filter are used for common mode. And which one of the following is the correct statement? Hard switching is preferred. No, obviously not. Soft switching is preferred. License is used to measure radiated EMI. No, license is a device to filter out that will not allow the noises from supply to the device under which is testing or device to supply. High power level is a main reason of EMI. No, definitely not. High power, high frequency will be a cause. And then CL filter is preferred when source has high and load has low impedance. Obviously, this is correct, right? So next, radiated EMI is measured using another one is the main reason for EMI powertrain converter. So try to answer this too. Fine, so I get two answers. So radiated EMI is measured using antennas, right? Antennas, you require antenna within your shielded room or screen room, right? I already discussed. So the main reason for EMI in power electronic converter, obviously parasitic capacitance. So long cables and there is no long cable within converter. Switched voltage and switched current, obviously that introduce transient noise. So these are the probable reason for EMI in power electronic converter. Okay. So this is the last question. So you use a T filter for EMI reduction when source impedance is dash and the load impedance is dash. How is one? How much? Okay, so the last question, and if you have any doubt, you can ask regarding EMI. Okay, try to answer it. I think that these are the questions which will help you all to solve the assignment of this week. And fine. So obviously low and low impedance is required. So this is the answer. So if you have any doubt regarding these classes, you can ask. Otherwise, we already done. If you have any doubt regarding the EMI, you can ask me. And that's all for the day. Uh, Good night, everyone. So if you have any doubt, you can ask. Otherwise, you can leave. Yeah, welcome. Good night. We'll meet in the next class. Yeah, as I show you a pi filter, there is a different configuration that is T filter. I I show it over there, right? That is a pi filter configuration. So that is T filter configuration. Okay. Anything else?
Sir, T filter source impedance is low and load impedance high, kada, sir.
Okay, you wait. I'm asking.
Sir, T filter. Sir, one small doubt, sir.
What was your doubt?
Sir,
Yes, yes. Sorry, network issue, so that's why I was saying that 5 minutes. Tell me, what was your doubt? Hello?
hello, sir.
Yes, yes.
Sir, in T filter, source impedance will be low and load impedance will be high, no, sir.
That is for pi, right? I give T.
Okay, for pi, source impedance will be low and load impedance will be high, yeah, sir.
Yes, yes.
Okay, sir. Sir, another one doubt, sir.
Yes. Yes. What is your another doubt?
Sir, the main reason for EMI in power electronic converters, sir.
I already discussed, right? In the slide I showed. It's the main reason
Sir,
for.
we can't take. Sir, long cables can be used as antenna
In which converter you see antenna?
in long cables.
Yeah. Tell me a converter where you are using antenna.
Sir, for picking noises.
Echoing noise.
Uh,
In my sense, I didn't know any converter having antennas. In wireless converters, we often use some kind of Wi-Fi or modules, but that doesn't require long cables, right? So if you require
okay,
antenna-like structure in your converter, you have to design it by traces. You have to design it by PCB layout trace. You have to do it in a serpentine manner to make antennas. But I don't know any antenna in any converter. If you know that converter, you can say me. Then you can check that and I can answer it.
okay, sir. Okay, sir.
So that's why we are talking about
Sir.
converter design and converter design in the sense the compact converter design in a PCB. So in a PCB, there is a no option of getting long cables. You can say about
Okay, sir.
long traces, but no long cable will be there. We are not talking about converters we are designing in breadboard or in some way. We're talking about converter design in a compact PCB that way. Whenever you're buying a converter from a marketplace, should we look like that? Okay.
Okay, sir. Okay, sir. Thank you, sir.
Okay. Any more questions?
No, sir. No doubts, sir.
Okay. Okay.
Thank you,
Okay.
sir.
Then you can leave. That's all for the day. Okay.
Okay, sir.